So in this final lecture of lesson 2, we now want to prove that the halting problem is in fact undecidable. And we will do this via a very nice diagonalization argument. So recall that the halting problem K was defined to be the set of all pairs E, W, coded as a single natural number, such that the eth machine halts on input W. Note first that the halting problem K is actually semi-decidable, or recursively enumerable. So recall what this means, being semi-decidable. Well, this means that there exists a machine that recognizes precisely the positive instances. So a machine that halts on all inputs that are in the set and does not halt on any input that is not in the set. But such a machine is exactly the universal Turing machine. So Turing machine U, right? Recall a universal machine on input EW, coded as a pair, does exactly compute the eth machine on input W. So if this halts, right, then EW, the pair, is in K, but this means U halts on this input. On the other hand, if it does not halt, then this is not in K, but since U simulates exactly what ME does on input W, it will also not halt. So this witnesses the semi-decidability or recursive enumerability of the halting problem. So the halting problem is positively decidable in the sense that we can list the positive instances, but as we will see now, it is not fully decidable in the sense that we cannot do this decide after a finite amount of time by telling yes, it is in, or no, it's not in. We will actually show that a variant of the halting problem, namely the diagonal halting problem, is undecidable. So the diagonal halting problem is the set of all x such that the x Turing machine on input x halts. So that's why it's called the diagonal. You take only from each Turing machine, you look at one instance of halting or not halting along the diagonal of all lists of Turing machines. Note that if the diagonal halting problem KD is undecidable, then K must also be undecidable, because if K were decidable, we could easily modify our algorithm to decide K to also decide KD. Right? That should be clear. So again, the undecidability of KD implies the undecidability of K. So here's the theorem we want to prove. KD is undecidable. Assume now for a contradiction that there exists a Turing machine M that decides KD. So that means whenever I input X to M, it halts and outputs 1 if the xth Turing machine on input X halts, and in output 0 if it does not halt. Right? So that computes the characteristic function of our set KD. Note that M halts in fact on every input, right? It always outputs something, either 1 or 0. And now comes the crucial part of the proof. Using our machine M, so the assumption that M exists, we can use the Church-Turing thesis to define a new Turing machine, M bar, that behaves as follows. on input x, m bar looks whether m of x outputs 0 or 1. If m of x outputs 1, it just simply decides not to stop. So that can be done by just making the machine m bar enter an infinite loop. We have seen how to do this, and it's easy to do this, right? The machine simulates m, right, on input x, and if once m outputs 1 on input x, it just enters an infinite loop. If, on the other hand, m of x is 0, so m outputs 0 on input x, it just outputs 1, right? So it stops and outputs 1. Now, m bar is a Turing machine, but every Turing machine has an index, so hence it has an index or Gödel number. So Gödel number, say E bar. So that means m bar is the same as m sub E bar, right? E is just the index of m bar in the listing of all Turing machines. And now we ask, well, this is an index, right? And we can now ask, is E bar in KD or not? In other words, does m E bar on input E bar halt? In that case, E bar would be in KD. Or does it not halt? In that case, E bar would not be in KD. So I've brought the two important definitions over to this slide. So m E bar of x is the same as m bar of x, which is undefined if m of x is 1, and is 1 if m of x is 0. Where recall that m of x, so m is the machine that decides the halting problem, the diagonal halting problem, which we assume to be decidable. That means it outputs 1 if m of x, m sub x of x converges, or 0 if m sub x of x does not converge, so does not hold. And we want to know now whether E bar is in the halting problem, diagonal halting problem, or not. So first suppose E bar is in KD. Well, that means that m of E bar is 1. Because recall, m was the machine that decides the diagonal halting problem. But this now means, for the definition of m bar, right, that m of x, so m of E bar is 1. That means m bar of E bar is undefined. And that in turn means that since E bar is the index of n bar, m sub E bar of E bar is undefined, which means that E bar is not in the diagonal halting problem. But this is just the contrary of our assumption, right, that E bar is in KD. So we must have that E bar is not in KD. But this implies now, right, if E bar is not in KD, this means that m of E bar is 0, right? Again, m is the machine that decides the, we assume to decide the diagonal halting problem, right? So that's 0. But if m of E bar is 0, then m bar of E bar is 1. So this means that m bar of E bar is 1. In particular, it halts, right? So it means that m of e bar, or e bar, halts and is equal to 1. But this means, in turn, that e bar is in KD, which is, again, the contrary of what we assumed. So we have a contradiction. So from the start, we get a contradiction to our assumption that KD is decidable. That is, our machine M cannot exist. So this here cannot exist. The halting problem was the first problem shown to be algorithmically undecidable. This was shown by Turing in 1936. These days we know many more examples of such undecidable problems. One famous example is the unsolvability, the question whether a Diophantine equation is solvable or not. That is an unsolvable problem, and that's also known as Hilbert's 10th problem. Hilbert's 10th problem. And this was shown to be undecidable, whether a given Diophantine equation has a solution in the integers or not. This was shown by Matyasiewicz, Robinson, Davis, and Putnam. A famous problem from algebra is the word problem for groups. And for us, an important undecidable problem or uncomputable function will be, and we will see that later, will be Kolmogorov complexity, which essentially is the problem of finding the shortest possible description with respect to a universal Turing machine of a given binary string.